particular worksheet, I'm going to maybe also add a little on the end of it to show you some technology to do this too. Because this is fairly abstract without the technology to help you, or a compass and a ruler at least. First of all, let me just talk about some new terms here. They talk about the circumcircle. The circumcircle is a circle that circumscribes a triangle. We knew that from earlier. And this is called the circumcenter. We'll see why. This guy is called the incircle because it's inside the triangle. And this is called the incenter. Circumcircle, circumcenter. Incircle, incenter. Now, how do you make these? That's the whole point of this lesson, this worksheet and the next one, but this group of lessons. You make a circumcircle by taking the three perpendicular bisectors of the triangle, and where they meet is the center of the circle that circumscribes that triangle. Over here, if you do the three angle bisectors of a triangle, they meet at one concurrent spot, and that spot is the incenter, which is the center of the incircle. So I want to just talk briefly about these two guys that make these up. The better we understand perpendicular bisectors and the better we understand angle bisectors, the better we'll understand why this works. So perpendicular bisector, perpendicular, 1, 2, bisector, goes to the midpoint. Now why this line is so important is anywhere on this line, we've learned in a previous unit in time, is exactly the same distance to this guy as it is to this guy. Now the reason is, if you want me to quick remind us of that, basically it's easy to prove that these are congruent triangles, therefore these are congruent lengths. Right? Side angle, side, side angle, side, they're congruent. Therefore, this is the same as this. And that would be true for any triangle along that line. Those guys would be also equal. Now again, why does that matter? Well, I'll kind of show you, but if you create one line that has all points that are the same distance from two endpoints, and you do it again from another location, where they meet has to be the same distance from that one to that one, and from the other two endpoints of the other side. So then they become equidistant to all of those points. That's why we get a circle. It's still foggy. I'll get to it. Over here, the relationship of an angle bisector is also that if you pick any point along an angle bisector, its unique relationship is that it becomes the same distance to the two sides. Now, why would that be? Well, again, these become congruent. An angle, a common side, a reflexive side, and what's our other known value? And the angle. Angle, angle, side, angle, angle, side, they're congruent. Because they're congruent triangles, they have corresponding parts that are congruent. These would be equal in length. So, why does that matter? Well, if you take an angle bisector of one of the angles, this one down here, anywhere along that line is the same distance to that side as it is to this one. Now, if you do that again from a different guy, let's say the angle bisector here, this line is equidistant to that side and to that side. And so now this point is equidistant to this side, and this side. It's got to be the center of a circle that can touch all three sides. I'm confused. Let's go to the computer and I'll show you kind of the construction, see if we can make more sense of it, okay? Wait a minute, I forgot to teach you one more thing before we go to the computer. Let's do that now. The other item that was on this little unit is this, and it's actually quite an important one. It's called the Inscribed Quadrilateral, which is what you expect it to be. All 4 points are on the circle that circumscribes it. Now there's a cool little relationship about the angles. They all add up to 360. That's not the cool thing. But opposite angles have a little bit of a relationship. I want to show you what it is. I want you to understand that the measure of angle, let's just use B, we don't need this here. The measure of angle B is half, let me use a different color here, is half of that arc, because angle B is inscribed on this arc. So it is half of the arc, measure of angle ADC divided by 2. It's half of that arc. Now watch this. The measure of angle D, the one that's opposite it, is half of this arc. So the measure of D inscribed is half of the measure of arc, we'll call it AC. This should be arc here. I don't know why I put that. Okay, divided by 2. Now, look at the green and the red. What do they make? One full circle. So this is interesting. If I put the measure of B and the measure of D, if I add them together, if I add these together, it will be equal to adding these things together, which is the measure of arc ADC added to the measure of arc AC divided by 2. Now this is getting out of hand. It looks like it's getting scary, but watch the cool trick right here. What does ADC and AC equal? ADC is the red, and AC is the green. Well, they together equal 360. So guess what? That is equal to 360, and 360 divided by 2 is 180. So we learned that in an inscribed quadrilateral, opposite angles, this guy right here and this guy right here, they will add up to 180. They're not 90 and 90 necessarily. They could be 20 and 160. They could be 100 and then the 80 and whatever. Now I didn't prove this, but it would also be true that this guy right here, this angle, and this angle over here, these two would also add up to 180. The premise is this, that one of the angles, inscribed angles, is looking at a part of the circle. The other inscribed angle is looking at the rest of the circle. And they are exactly half of what they're looking at, which is half of 360 is 180. So again, you don't need me to do this, but the easy part now becomes if they tell you this is 100 up here, this is 80 here. If they tell you that this is 60 here, this becomes 120 over there. Opposite angles in a inscribed quadrilateral will be equal. Now let's get to a little bit of quick constructions. This is going to be a long video. Yikes. All right, let's show you how to create a circumcenter or a circumcircle. And I'm just going to use kind of the technology tools to pull this off. Actually, let's label this. Let me show the label here so that we've got something to talk about. All right. And the first thing, I guess, this thing is made by perpendicular bisectors. Now, the geometry tool is going to skip some steps that we would do by construction, but I want to do the perpendicular, actually I want the perpendicular bisector between those two. So that's a perpendicular bisector. In other words, any point along that line is the same distance from C to A, sorry, from C to the line as B to the line. Now if we do that again from the other guy, anybody along this line is the same distance from A as it is to C. Now what's cool is that point then is the same distance to C as it is to B as it is to A. And that, of course, would make a good center of a circle. Now that thing can move around a little bit. And actually, what's even better to do, let's do it. If I do the last perpendicular bisector, guess what? They all meet together. So if I select these guys and say construct the intersection of this and this, I find it. Now, because that point is, because it's on this perpendicular bisector, equidistant to these, because it's on this one, equidistant to these, there is a circle. And you know how a circle works, is that it's the same distance to each point. So if I go to C, look what happens. I went through A and B as well. So check this out. That circle stays circumscribed around our guy there. And again, this is the circumcenter. All right, let's clean this up real quick here, and let's show you another cool guy to make. So if I create my triangle again, and this time our relationship is the angle bisectors. And so if I have my triangle here, and I do angle bisectors. So again, this is a construction, but in this case, I'm going to select my angle. Now that's the angle bisector of A. It's any point on here is the same distance to this side as it is to this side. If I do that again, I create a location that's the same distance between these two sides, but it's also the same distance between these two. So this is the same distance to all three sides. Now, as you would expect with concurrency, that guy goes to the same location. Very cool. So let's do a little intersection to get my incenter. This is called the incenter. Now, the only trick about getting the incircle, which is an absolutely gorgeous little construction once it's made, is that the distance from that to each side is equal. But it's also the perpendicular distance. It's not this guy. So like if you pull out and use a circle and go to like that point, you don't touch each side once. So what we need is a perpendicular line. Let's show you what I mean. I need a perpendicular line through this point to one of the sides. It does not matter which side. Now that will give me, and I'm going to place that point there if I can. If I grab my circle tool now and I go centered to here, look what happens. Gorgeous. See how it touches tangent to each of the sides. So watch what happens. If I adjust this, that little circle just stays tucked in there beautifully. That's called the incenter and the incircle. Cool stuff, isn't it?